This is a problem on the level 1 second-order transients problem, which will be problem type 1, which is a series LC circuit. So, as always, the introductory tutorial is a very good idea to view, especially on this topic. As it's a rather complicated topic, that'll be especially important to view the tutorial. I will, however, skip that here. And it's also a good idea to view some examples. So let's show you a little bit of an example at level 1 of this problem type. Now there is a special interface used for these examples because the full explanation at all the different times is a little bit involved, and it takes a couple of minutes to generate. So in order to give you a little bit more control over that, you have these options here. So you can control, for example, if you want to see the general solution strategy, which is unchecked by default, and then at each of the different times, which you would normally probably want to view all those if you're looking at an example. But you can also choose whether or not to see the individual steps in each simplification, for example, at the different times. You can either do none of it, which is the default, or you can do it at all times. And likewise, you have a choice, when applicable, whether or not you show the simplified form and matrix equations. Now that only applies, of course, when doing node or mesh analysis, but again, you can choose that not to see that at any time or to see it in every case. That's up to you, and you can adjust it for specific steps. So here, just for the sake of brevity, I'm going to just show a solution, for example, at one particular time. And it'll take a moment to generate that. So here we have the solution at that particular time, again showing the various steps that are involved at that time. And then if we want to replot showing additional or less information, then you can do that here. Okay, so I'm going to go ahead now and do an example of a problem. So again, we're going to do problem type 1 on the easy problem. This is one with series LC circuit. So here's an example of that circuit, and similar to the first order transient case, we have analysis that we have to do at various times, including t equals 0 minus, that's just before the switch is thrown, which is at t equals 0, at 0 plus, just after that switch has been thrown. But there's a special case also, which is we have to do some type of analysis here of the first derivative situation at 0 plus, which will not be very complicated on this level, but it'll be more complicated on the second level. And then we have to find the Thevenin seen from the terminals of the combined inductor and capacitor, which is what we assumed in the introductory tutorial here. Now, not all problems have these things in series or parallel, but those types of problems are not currently supported in Circuit Tutor. And finally then, analysis at infinity. And as usual, we can get written help here, and you can always give up at any point for no penalty. So let's begin by analyzing. Generally, you want to do these things in chronological order. At least that's the simplest way to do it. So I'm going to start out with the analysis at t equals 0 minus, just before the switch is thrown. So by clicking that, it's going to change the labeling for me on the variable. SOT variable, for example, here is now at 0 minus. And notice my SOT variable in this case is the inductor current, which is also the capacitor current, but it's labeled here as being the inductor current. And of course, it's also that of the capacitor because they're in series, as I showed you. Okay, so then basically we start by reconfiguring the circuit, which is similar to the first order case. And if you haven't done the first order problems, it's probably best to start with those before embarking on the second order. But in any case, I'll show this as if you haven't seen the first order. Okay, so it'll bring up some instructions initially, which I don't need here. So, and now basically we need to reconfigure. So that means we need to change the circuit such that it'll be appropriate for analysis at 0 minus. So one of the things we have to change is the switches. So here the switch is opening at t equals 0. So at 0 minus, before that switch opens, that switch will be equivalent to a short. So we're going to change that to a short. And of course, if it had been the other type of switch which was closing, then it would have been an open circuit, which we could expressed just by deleting the switch and replacing it by an open circuit. Okay, then the other thing that we need to change here, we will need an additional SOT variable, because in second-order circuits it's always necessary to find both the inductor current and the capacitor voltage at t equals 0 minus, because those are the only two things that are going to carry over directly to 0 plus. Because remember, the inductor current cannot change suddenly, because that would give us infinite voltage across the inductor. And likewise, the capacitor current cannot change suddenly, because that would give us an infinite current through the capacitor, just by the fact that V equals L di dt for an inductor and I equals C dV dt for a capacitor. So I'm going to place here a SOT variable on the capacitor, which would be the voltage at 0 minus. That's the only thing that's going to be preserved, so there's really no advantage to calculating anything else. And so I'm going to add a SOT variable there with the positive sign on the right, just to keep that consistent with the passive sign convention with respect to the inductor current. Just makes it a little bit simpler. Not necessary to do that, but I prefer to do it that way. Okay, so having added, and we already had this SOT variable in this case, but we had to add this one. And so now we're going to change the inductor and the capacitor to be their steady state equivalents, because the assumption generally at 0 minus is that the switch had been in its position for a long time prior to t equals 0 before being switched. And therefore things would have come to steady state, assuming it's a stable circuit, and therefore all transients would have died out. And therefore in steady state we know the inductor is equivalent to a short circuit, so I'm going to change that to a short. Oh, I'm sorry, I had the wrong element selected there. That was my bad. I meant to select the inductor, so I'll change that to a short. And it was showing me an error actually, because I tried to change the capacitor to a short, which was not intentional in that case. But the capacitor, of course, is going to be an open circuit, so I'm going to change that here. In order to preserve the SOT variable, I need to change it to terminals. If I try to delete it, it'll just give me an error, because then the SOT variable wouldn't be there anymore. So I'm going to use the terminals here to represent the open circuit of the capacitor. Okay, and if you needed to start over at any point, you could hit restore circuit, and in your case you'll also have an option for both help and video help once the video help has been recorded. Okay, so we're done reconfiguring the circuit, and now let's analyze that circuit and see how we could figure that out. The IL of 0 minus is going to be obvious, because it's dangling basically. The inductor is dangling. The voltage here, however, is not going to be so trivial, so it makes sense then to simplify the circuit a little bit. So this gives me the instructions for simplification, which I don't need right now. And basically it's going to be as you usually do. We can combine the two resistors in series, so I'll make that 17 ohms there, and change this one to a short, which is what we do in combining resistors, so that the total resistance is still 17 ohms. Remember, you never change this to an open in series, because that would imply infinite ohms, which wouldn't be correct. So we'll check that, check the combination, and that is correct. And now we notice that we have the 17 ohm is now in series, in parallel with the 3 ohm resistor being connected to the same pair of nodes, and so I can basically use the reciprocal formula to compute that. I take 1 over 3 plus 1 over 17 and take the reciprocal of that, and that works out to be 2.55 ohms, so I'll put that in there. And then I'll remove the other one, which I want to replace by an open circuit now. And so that's takes care of that, and I'll check that answer. And another thing that might be a little less obvious to you here is that this resistor is actually in parallel with a voltage source. And because of that, you may remember that resistors in parallel with a voltage source are basically what we call redundant or voltage splittable, meaning that they don't have any effect on the rest of the circuit, on the SOT variables, for example. The only thing that resistor does affect is the current out of this voltage source and its power that it's supplying to the circuit. But since we're not interested in either of those things here, we can safely just delete that resistor, and that'll make the circuit even simpler to solve. So it's told us that we've correctly removed a voltage splittable element, which is the same thing as a redundant element. And that's basically as much as we can do here. So we're done editing. And now actually it turns out that these values are fairly trivial. So now I'm going to use single loop analysis, which is also appropriate if there's no complete loop in the circuit, which is the case here. Everything is basically what we call dangling, or you might call that hinged. So I'm just going to directly calculate that sought current because that's very easy. I don't need Ohm's law or anything like that. I simply recognize that because there's nowhere for that current to go, that current must be 0. So I'll select 0 as my answer there and check that. And that is correct. And then furthermore, because this resistor is also dangling, we know that it can't have any current. There is no complete path for current to exist in this circuit. And so the current through this resistor must be 0. Therefore, its voltage drop, which is V equals IR, is also 0, meaning that the resistor in effect is virtually the same as a short circuit. Now you're not allowed to change it to a short circuit in the circuit editor, but it can be ignored here. And so basically we see the 4-volt source is in effect directly connected across VC of 0 minus, which is where the capacitor was here. The only thing to note is, very importantly however, is the positive side here is connected to the negative side here, and the negative side to the positive side, meaning the polarity is inverted. So I'm going to select a sought branch voltage there because that is considered a branch voltage because there's sort of an invisible 0 value current source there. And so that value will be a fixed voltage. As I said, that's going to be negative 4 volts rather than positive 4 volts, again, because of the polarity issue here where that polarity is mismatched. So we'll check that. And indeed, that is correct. So we're done finding our sought variables. And that completes the analysis at 0 minus. Now, the next step would be to analyze at 0 plus. And you may remember that in first-order transients, it isn't always necessary to do a detailed analysis at 0 plus, but in second-order circuits, it actually is. It's always necessary to do that analysis. And so we're going to go ahead and do that. And so instead of just asking us for one particular parameter, which we could easily find, we're going to have to actually analyze the circuit. So basically, it's relabeled here, IL of 0 plus and VC of 0 plus now. And then we're going to do the rest by reconfiguring the circuit. So we click Reconfigure Circuit, which we normally do here. And remember that we are not in steady state at 0 plus because we've just opened that switch. And since the switch has just been opened, that exerts a change on the circuit, which means it's not in steady state at all. And so it would be a mistake, for example, to assume that the inductor is a short circuit or that the capacitor is an open circuit. That's not true at 0 plus, even though it was true at 0 minus when we were in steady state. So the first thing I'll do, which you always need to do when you're reconfiguring, is to replace the switch by the appropriate equivalent. Now, since 0 plus is of course after the switch has opened, so now that switch is actually open, which means I will simply delete it. So I can either hit the delete key here, I can use the key on my keyboard, or I could right click and hit delete here, for example. Any of those 3 methods will work. Okay, so we've done that successfully, and now you might think that we're done, but we're not, because again, the inductor, we have to think about what do we know about the inductor at t equals 0 plus. And of course, we know that the inductor current cannot change suddenly, that IL of 0 plus must equal IL of 0 minus. So therefore, the inductor really has 0 current. In other words, it can be replaced, as we would often do in a first-order circuit, by a current source, but in this case, the value of that current source is 0 amps, because it's a 0 valued current source, based on what we found out at 0 minus. So in order to do that, but before we do that actually, we have to add a sought variable, because one of the things we have to do in a second-order circuit that you don't have to do in first-order circuits is you have to find more than just the value of IL of 0 plus. We also need to find the first derivative of IL at 0 plus. And in order to get that, I'm actually going to need the value of the inductor voltage at 0 plus. So I'm going to add that voltage as a new sought variable. And again, you have to know to do this basically. And if you don't do it, then it'll basically give you an error and tell you that you have to do that. And that's something that you need to remember, that that's required in order to solve this type of problem. So we're going to add a, again, I'm going to use passive sign convention here just to avoid unnecessary minus signs. Now, you could use active sign convention with the current going into the negative sign, but personally, I like to always use the passive sign convention where I have a choice. Okay, so having done that now, I need to keep that sought voltage, but I also want to change this to a zero-valued current source. Well, remember, a zero-valued current source is really the same as an open circuit. Now, I can't delete the inductor because that would get rid of my sought voltage. So instead, what I do is I use these terminals, which allow you to maintain a sought voltage in Circuit Tutor. It basically gives you a place to draw it. So we do that, and we still have, and the current went away because we know that that doesn't change. And that's expressed already by the fact that it's an open circuit. Okay, so now for the capacitor, technically in this case we don't necessarily need its current because our sought voltage is actually the inductor voltage, but just to be on the safe side, I'm going to define a sought current for the capacitor, because in some types of problems you would actually need that. So I don't actually have to do this here, but I'm just going to do it anyway. It's not a big deal. So I'm going to make that again using, once again, passive sign convention, where I'm going to have that current going into the positive side of the capacitor voltage. And then I have to say, well, what do I know about the capacitor? Well, I know it has a fixed voltage at 0 plus, which is the same as its voltage at 0 minus. And because I know its voltage, that means for all intents and purposes, it's the same as a voltage source with that voltage of -4. Now the -4 applies based on the polarity we had originally chosen for VC of 0 minus, which had the positive side on the right. So I'm going to change it to a voltage source now. And remember, it would not be correct to assume that's an open circuit because we're not in steady state here. Now, notice that this has the opposite polarity and it's written up here that VC had the positive voltage on the right. So, but I actually want to change the polarity here because that has a negative voltage. So I'm going to keep that the way it is and change this to positive 4 volts. So I'm basically changing both the sign of this voltage and then the polarity of the source to match. And that way I avoid the negative signs. So that would be the equivalent of my capacitor as a voltage source and the inductor as a zero-valued current source. So that basically means I'm done reconfiguring this circuit. So I'm going to click Done there. And that was all correct. Didn't give me any error messages. And so now I have to analyze this. And of course this IC of 0 plus, that's rather trivial because that's a dangling voltage source. So therefore that really doesn't do anything here. So I know that that's going to be identically 0. So the more difficult part is the voltage across the inductor, which is now across the combination of voltage source and a resistor. So that will require a little bit of circuit analysis. So let's go in and simplify the circuit just to make that easier. Make it a little bit easier anyway. Now, notice you may say, well, I have actually 4 resistors. If you're astute, you might notice all 4 of those are in series. However, they're not all combinable in series because the problem is that I also want to know this voltage from here to here, which basically is essentially from here to here. Well, it does include this voltage source, actually. That does play a role in it. But I basically need to know the voltage from here to here, and then I can find the voltage from here to here. And because I need that, that means that I cannot combine this resistor with the others because that would change the value of that voltage. In other words, the voltage across this resistor is going to be part of the voltage from here to here, but the voltage of these other 3 will not. So this one is not combinable with the other 3. However, I can combine the other 3, and so that's 9 plus 8 is 17 plus 2 is 19, so I can make that 19 ohms there. And then I change this one to a short and this one to a short. But again, I cannot combine it with this one. Even though it's technically in series, it's not combinable because of the fact that I have this sought variable. And that's very important. Remember, sought variables can determine what you're allowed to simplify and what you're not allowed to simplify. So we'll check that, and that is correct. And now we don't have any elements that are redundant. Again, this voltage source is technically dangling, but we need the voltage here, so we can't remove that because that would not allow us to find this voltage anymore. So we have to keep everything that's there now. So we're basically done with the editing. Okay, so now we have only a single loop in the circuit, so we could use, for example, single loop analysis as our analysis method. And so basically, let's do the current first because that's very easy. So the sought branch current for the capacitor, because that is dangling on one end, that's got to be identically 0. So we just put 0 there, and that is correct. Again, there's just no complete path for that current to exist in. And next we have to find the voltage basically from here to here. So that's a little bit more involved. And so let's do a sought branch voltage. And now basically are going to need to say, well, we can take a path, for example, going from here to here, and add up the voltage drops along that path. So my voltage here is going to be equal to, first of all, because this has a negative sign on this side, that would be -4. Okay, because that's actually going from the plus to the minus, that's actually going up, so it should be negative because I'm actually counting the drop as I go this way. And now I want the voltage drop across the 3 ohm, so by Ohm's law, that's going to be I1 times the 3 ohm. Notice I haven't prepared to calculate I1 yet, but I'll do that before I'm done here. And then finally, to go from here over to here, now I have a drop of 4 volts. And that's consistent with this polarity, and so therefore now I'm actually adding the 4 volts. So you might notice that really I could leave those two terms out because they're going to cancel each other. I'll just leave them in, but you could, if you do remove them, it'll count that as correct, because in this case they do happen to cancel each other out. But of course, if one of them had a different value, then that wouldn't be the case. So it's a little bit special here. Okay, so we'll check that. And that is indeed correct, but now I still need a KVL equation for this mesh so that I can actually find the value of I1. So I'm going to go and put in the KVL equation, and I could have done this first, it doesn't really matter. So now I have basically a current times a resistance, and I could use two terms there. I guess we'll just do that. We could also combine them into one term if you like, but I'll just use two terms. And then we have a voltage drop across the 4 volt source, and then all that is going to add to 0. So I'll prepare those terms. So first of all, just starting, say, from the lower left, going through this resistor, that's I1 times 19 ohms. So yeah, I1 times 19. And then, well, I could rearrange those, I guess, to put them in order. Doesn't matter. And then I have a voltage rise of 4 volts, so that becomes a negative drop since I'm adding my voltage drops going in the direction of the mesh current, going clockwise. And then finally the voltage drop across the 3 ohm will be I1 times 3 ohms. And again, it doesn't really matter what order you put these in, I just made that in that order for clarity. Okay, so now we have all the equations that we need. So I'm going to hit no more equations, and now it's just asking me to calculate I1. And that's a fairly simple calculation because we see we're going to have basically 22 times I1 equals 4. So I1 will be equal to 4 divided by 22. So you can almost do that in your head, or 2 divided by 11, really, 2 elevenths. So if we work that out on a calculator, say, as 2 elevenths, that will turn out to be 0.182. Of course, you won't have the cheat button there, but I have that. And we'll check that, and that's correct. And now I need to calculate my sought variable. Now I've already done the current, so that's kind of grayed out there. I don't need to really enter that. In fact, I can't. But I'm going to enter this voltage, so I just take my value of I1, which is the 0.1818, and plug that into this equation here. And so that basically, just because these terms cancel, it's just basically multiplying that by 3. And so once again, that's just going to work out to 0.5455 volts. So we'll check that. And that completes the calculation at 0 plus. So basically it's summarizing all the work that I've done up until now. So now I have to do some analysis to get the first derivative of the inductor current at 0 plus. And so that's the next button here. In this case, that's going to be fairly straightforward. But let's think about how you can actually do that. So you say, well, I don't know what IL prime is, but we do know that for an inductor, that V equals L di dt, right? V equals L di dt. That's the basic formula for an inductor, assuming passive sign convention here. And that's what I'm going to be using since that's how this was defined. Remember, I defined VL with a positive sign on the top, so I'm confirming there that that is in fact passive sign convention. Had I defined it with active sign convention, then I'd have to put a negative sign into that equation. What that means then is that I can compute the IL prime, which is the IL dt, just by taking the inductor voltage and dividing it by the inductance, which is 5 henries. So I just basically take the inductor voltage, and this is why I had to find that inductor voltage. Now notice I'm not going to actually use this value here in this particular circuit, but in some circuits I would though, so that's why I just went ahead and calculated that. It wasn't really any extra work anyway. So just take this, divide that by 5, and so it asked me for the value of the first derivative of the inductor current at 0 plus, and now the units here are going to be amperes per second. So I'm going to go ahead and enter that, and that's going to be just a little bit over 0.1, as you can see by dividing that by 5. So that's the value there, and that is correct. So that's all we need to do here at for the first derivative situation in this circuit, although in other circuits it may be more complicated. Now the next thing I need to do is to find the Thevenin equivalent resistance, and remember this is what's going to be seen from the combination of the inductor and the capacitor, and that's how we actually derived the general form of the solution that we discussed in the introductory tutorial, which I'm not going through here. I'm assuming that you've hopefully read that. So to find our Thevenin here, again I'm going to follow the usual steps of reconfiguring and then basically analyzing the circuit. So let's click the reconfigure button. And so now I'm in the reconfiguration mode, as it says here in the circuit editor. It always tells you at the top here. It also tells you what you need to do in that mode, in case you've forgotten. So remember that one of the things we always have to do in this mode is to set the switches to the appropriate equivalent. And again, because we're only interested in this time constant for t greater than 0. Remember, we're trying to find a transient when t is greater than 0, not when t is less than 0. That transient with t less than 0 would have a different time constant, very likely, and that one was died out before we started, so we don't really care too much about that one in this problem. So therefore we're analyzing this for t greater than 0. That's important to remember. So that means that this switch is open, so I'm going to just hit the delete key on my keyboard and just get rid of the switch, and that's the correct action there. Okay, so now what I need to do is to look out from the terminals of these two things in series. You say, well, how do you do that? Well, basically, we're going to, in Circuit Tutor, what we're going to do is we're going to change one of those to a set of terminals. It doesn't matter which one, you can pick either one. And you also notice that there are no dependent sources here. In fact, none of these problems are actually going to have dependent sources in the second-order transients. So basically that means I can use resistive simplification since there's no dependent sources. So I'm going to change that to terminals. And then you say, well, how are we going to make these terminals see the entire resistance? They wouldn't see it now because there's a capacitor in the way. So I'm going to basically change that capacitor to a short circuit. And that way, these terminals basically have replaced the combined inductor and capacitor. And I could have done it the other way. I could have made these in terminals and made this a short circuit. Either of those ways will work, but one way or another we have to be seeing what the inductor and capacitor together would have seen from their combined terminals. That is from here to here, basically. Now there's one last thing I can also do while I'm here, and that is to do some source killing. Now remember that when you're trying to see a resistance, you don't want any independent sources active unless you had introduced a test source in place of the element you're measuring. And we don't. Only time we do that is when we have a dependent source, which again is not going to apply in these problems. So there's basically this source therefore needs to be deactivated or killed, and because it's a voltage source, we want it to have 0 voltage, which means it needs to be equivalent to a short circuit. So I'm just going to change that to a short, and that is correct. And now I'm done reconfiguring it. Remember, I'm not allowed to simplify in this mode, so I have to go in and out of the circuit editor to do that. Okay, so now if you can see the value by inspection, you can just enter it if you like, but in this case it's maybe not so trivial, so I'm going to simplify the circuit. And now I have these three resistors in series. Remember again, once again, this is not in series with the other three, and that's because this time, because of these terminals. Remember that when you're viewing a resistance, you're basically putting a multimeter out here, which either applies a voltage and measures a current, or it applies a current and measures a voltage, one or the other, or something, maybe even another method, but that's typical methods, which means that there's going to be current going through here and coming back here, for example. So these are not in series. Okay, so only these three are in series. This goes back to the ideas that we covered in the series parallel with terminals tutorial originally. So we have a total of 17 plus 2 is 19 ohms. So I'll just put 19 there, and then I can change these others to shorts. Doesn't matter which one you change, just as long as two of them are gone as shorts basically, and we'll keep the remainder. We'll check that. And now I can combine these other two, notice, are in parallel. So the presence of the multimeter here doesn't change the parallel relationship because they're connected to the same two nodes. So now I can use product over the sum rule, for example, 19 times 3 divided by 19 plus 3, which is 22. So working that out on a calculator, I can get the equivalent resistance using the product over the sum rule for parallel resistors, for two of them anyway. And that works out to be 2.591 ohms. And then this one, of course, needs to be deleted so that I'm only seeing the equivalent from the input terminals. Okay, so we can check that. And that is indeed correct. And now, since I just have one resistor left, I can just basically record the Thevenin value. That's only available when you have just one resistor here. But since I do, I can just do that instead of having to actually go out of the circuit editor and then enter it that way. Just a little bit quicker to do it here. And that'll automatically take me out of the circuit editor because I'm done basically determining that parameter. Okay, so I've found all the parameters we need except for the value of the SOT variable at infinity. So that's my last task here. So I'll click on that. And once again, it's going to change the labeling. So now this is called IL of infinity. Remember, it should not be labeled IL of t because this is only going to be valid at IL of infinity. So if you're doing this on paper, you want to make sure to label these appropriately, and that would be IL of infinity in this case. Okay, so we're going to reconfigure that circuit, as we always have to do. And as usual, the first task is to take care of the switches. So once again, because we are at infinity, that means we're after t equals 0. So this switch, therefore, is going to be open. So I can replace that by a simple open circuit. So once again, I'm just going to click the delete key on my keyboard, and poof, it goes away. Then the next thing here is I have to treat the inductor and the capacitor. And remember that at t equals infinity, that's a long time from now, of course, and therefore everything in a stable circuit will have come to steady state once again, just like at 0 minus and at 0 infinity. Those two times we're in steady state. So being in steady state, you need to remember that because V equals LdI to t for an inductor, that means that since nothing is changing in time, the V will be 0, meaning that it's basically a short circuit. So it's going to be a zero valued voltage source, or equivalently a short circuit. So I can just change it to that. Now, on the other hand, the capacitor in steady state, remember there the equation is the dual of the inductor equation, namely it's I equals C dV dt. So the time derivative is once again 0 because we're in steady state. All time derivatives are 0 in steady state. And so now the capacitor is described by the fact that its current is 0. In other words, it's zero valued current source. And because it doesn't have a SOT variable here, I can just delete it. Okay. The reason I keep these terminals is basically to put a SOT voltage across it. So it's simpler just to delete it. And we'll leave this dangling here. Okay, so that's basically all we need to do. And again, of course, there's no source killing down at infinity because we need these sources active to find the value. Although actually in this case, it doesn't really matter, but normally you would leave that active. Okay, so in this case, there's really no point in simplifying the circuit because we know just by inspection that this current has nowhere to go. Therefore, it has to be 0 no matter what's going on in the rest of the circuit. So it's simple to just go ahead and analyze it without even bothering to simplify. I mean, you can simplify if you like, but it's not really necessary. So we have a single loop here. And I will enter my IL of infinity directly as being 0. And if you think about it, when you have a series LC circuit, that's always going to be the case for the inductor current, because basically it's going to be in series with a capacitor, which is going to be an open circuit at infinity. So all of these problems are going to have IL of infinity being 0 if they're in series. Now in parallel, of course, that would be different. And you can think about what would be 0 in that case. Okay, so we'll check that. And that is correct. And we're all done there, so no more equations. And now it's going to bring us back to the original circuit. It's taking its time here for a minute. I guess it's thinking. Okay, so here's a summary of what we've done. Now this information would not be shown to you, so don't expect to have that, but basically we're going to need to do the calculations that are indicated down there. So what we need to do now is we need to enter the final transient expression. So it's a second order transient expression, so we just select that. And it will pop up here with some helpful equations. You will need these equations to do the calculations. Without these, you'd have to have a very good memory. So there's a lot of equations involved. Now remember that we are dealing with a series R Thevenin LC circuit, and so we're going to use, for example, this formula for zeta. We'll be needing these formulas. So now I'm going to form the general form of the solution. So IL of t is going to be equal to something. Well, first of all, the constant term would be applicable if I have a value at infinity. Well, remember that we found out that the value of the inductor current in this case is actually 0 at infinity. So therefore, the particular solution is 0, and we don't actually need this term. I mean, you could, and it won't even allow you to enter a 0 value there if you added that term. So we don't even want to add that. However, to know what else we actually have a choice of 3 different terms here for the transient term. So this one is basically a simple exponential decay with a constant prefactor, and you can choose the units to be appropriate. This one is an exponential, but it's multiplied by a t prefactor, and so that's, as you may remember, that applies when you're critically damped. And then this is a decaying exponential multiplying a phase-shifted cosine, and as you may remember, that's appropriate when you're in an underdamped circuit. So you say, well, how do we know which of these to use? Well, that's where we have to find our damping factor, and that's the first task that we're going to have to do. So basically, we have to pick the correct formula here, which is R Thevenin over 2, the square root of C over L. And our R Thevenin here was 2.591 ohms. And the C here was a 1 farad, so that's just 1, and then the L is 5 henries. So we basically just plug those numbers in and do that numerical calculation. And what you can show then is that that will work out to be 0.5793. Like I said, that's not going to be shown to you, but you would have to do that calculation, which is a simple numerical calculation. And you should also check that this is in fact dimensionless, as shown here, because an ohm times a square root of a farad or henry, that does work out, as shown in the introductory tutorial, for example, to be a simple dimensionless, or 1. Okay, so based on the fact we're underdamped, well, we can now choose the form of the transient solution. It has to be this. And we could also go ahead and put in the units. It's basically choosing one term here for units that are either current, voltage, or power. So we're going to enter it because we know it's a current. This has to have units of amperes. Okay, but for the parameters now, we're going to have to do some more calculations. And again, using these formulas. So basically, come over here and bring up the algebra that I've already worked out on this. So the general form, generally for applying initial conditions, remember that there's several different forms here that are shown. So the initial form assumes exponentials with frequencies S1 and S2, which may be complex numbers. In fact, they are complex numbers in this case. And then we have the coefficients K1 and K2, and then we also have the value of the parameter, which in this case is the inductor current at infinity. Now we know in our case, that's actually 0. And that applies in everything except the critically damped case where you have to use the second form that has the t here. Remember, if the S1 and S2 are equal, then these are no longer linearly independent functions as they need to be, and therefore you have to introduce this type of term for the critically damped case, but that's quite rare. Now, as shown in the introductory tutorial, we can convert this over to this type of form, basically using the Euler identity. So for example, when we calculate S1 and S2 here, it turns out that those are going to be complex values in this case. How do I know those are complex? Well, just look at the formula for S1 and S2. And remember that zeta is less than 1, as we've already determined. So when zeta is less than 1, the square root is going to be the square root of a negative number, because zeta squared, of course, will be less than 1. Therefore, subtracting 1, that's going to be negative. That means that this is going to be purely imaginary. And then we also have the real part here of just the value of zeta. So that means we're going to have full complex values for S1 and S2. The real part will normally be negative, which is what we'd expect for a stable system. So because we're going to have complex values here, it makes sense then to use the Euler identities to take the e to the S1t and say that that, remember, is equal to cosine S1t plus j times sine of S1t. And then you can do the same thing for the S2 term. That's cosine of S2t plus j times the sine of S2t. And basically then combining the different cosine and sine terms together, we can put it into this form, where we basically grouped the S1 and S2. And also I've used the fact that the S1 and S2 can be written as negative sigma plus or minus j omega d. And that's the damped resonant frequency, which is given by the undamped natural frequency omega naught times the square root of 1 minus zeta squared. So I haven't shown all these calculations here because they're mostly pretty straightforward. The calculation of omega naught is 1 over the square root of LC, so that's just 1 over the square root of 5 times 1 in this case, so 1 over the square root of 5. So you can work that out. And then we multiply that by the square root of 1 minus zeta squared here to get omega d. And as I said, if you do that on paper, you'll find that the sigma here is going to be 0.2591 numbers per second. That's the sigma is this zeta times omega naught. And then the omega naught is 0.4472 radians per second. And then omega d is going to be a little bit less than that, which is 0.3645. So again, that's using this formula to evaluate those numbers. So that's something you'd have to do on paper. And I didn't show it here because it's just simple arithmetic. Okay, so having determined those parameters then, we know that these are going to be, as I said, complex constants, and so we can put it into this form, combining basically the A1 is K1 plus K2, and the A2 is going to be B1, I'm sorry, it's going to be K1 minus JK2. So these A1 and A2 are going to be real numbers. And so now, to apply initial conditions, basically I'm going to use this form. Now we also have taken this form and used a trig identity to put it into a single exponential, exponential times a cosine function with a phase shift. So this is equivalent to this form, but I think it may be a little bit easier to use this form when you're applying your initial conditions. Now if you'd rather use this, you can, but I'm just going to demonstrate it using this. So I'm going to take my current in this form of e to the negative sigma t times a1 cosine omega dt plus a2 sine omega dt plus il of infinity, although we know that that's actually 0 in this case. And the first initial condition is il of 0 plus. So we calculated that was up here, that's 0 amperes. And so therefore, we just have to evaluate this at t equals 0. And of course, e to the negative sigma times 0, well, that's e to the 0, which as we know is 1. So this basically goes away. And then the sine of 0, we know is 0. So that basically wipes out that term. And the cosine of 0 is 1. So that just leaves us with a simple a1 for this expression. So just evaluating this again at t equals 0, just gives us the A1, because again, the exponential is 1, the cosine is 1, and the sine is 0. So that A1, in fact, has to be 0 here, because we found that the IL of 0 was, in fact, 0 in this particular problem. That won't always be the case, but it was here. So that gives us one of those two parameters, A1 and A2 coefficients. And now the second one has to be determined by the first derivative condition. So we're going to take the first derivative of this expression. Now that's a little bit complicated, of course, because we have basically a product of an exponential with either a cosine or a sine. And so that means we're going to have to use the product rule as well as the chain rule in evaluating this derivative. And so I've done that down here. And so basically, if we take the exponential and just copy that down, well, actually, let's differentiate that, I guess, in the first term. So let's just differentiate the exponential. So using the chain rule, that brings down a negative sigma in front. And then this part, we're not going to differentiate using the standard product rule. And then the second part will be to just copy this down, as I did here, and then to differentiate this with respect to time. So the derivative of cosine omega dt, well, that's going to be negative sine, but we also have to bring out a factor of omega d using the chain rule. So we have negative omega d, still of course have the constant a1, and then we have the sine of omega dt. And then differentiating this term, the derivative of sine is of course cosine, and so that'll give us our cosine of omega dt, but then using the chain rule, we also have to bring out a factor of omega d, so that comes out front here, and then of course, we still have the constant A2. So we actually get a total of 4 terms here, but that's going to simplify a great deal because remember what we're interested in is, sorry, there's a misprint here. That should be IL prime of 0 plus. My apologies for that. That's IL prime, not IL at 0 plus. IL 0 plus is up here. So evaluating this expression, the derivative at 0, the exponential here is e to the 0, so that just goes away, and we have just a negative sigma out front. And then here, now the sine of 0 is again 0, and the cosine of 0 is again 1. So inside the bracket, we just have a1. So we're going to have minus sigma times a1, that's the first term. And we actually computed a1 in this problem as being 0, so that term is actually just going to go away entirely. Then for the next two terms, we have, again, the exponential e to the negative 0 is 1. So that goes away entirely. And then the sine of 0 is, of course, again 0. So that term goes away completely. And then the cosine of omega dt, when t is 0, that becomes cosine of 0. So that becomes 1. And so this is the only part that survives, basically, is the omega d times a2. So that's what we have. So out of all these 4 terms, we basically just get this. And this part goes away in this problem because a1 was 0. And my omega d I2 now, A2, we already had calculated the IL prime, again that's a prime there, of 0 plus, and that, remember, was 0.1091 amperes per second. So I put that over here, and then this is very simple, we just divide this number by the omega d, which again, we'd already calculated that just from the other numbers that were provided as 0.3645. And dividing that just gives us 0.2993. So that's the value of A2. So now we have our values of A1 and A2. And so that means we can go ahead and enter those. And so now, but the thing is we don't have a term here that has A1 and A2. So this term actually is the term in this form, which is really how we want our final answer. So we have to remember that according to the identity that converts this to this, the a is the square root of a1 squared plus a2 squared. So that basically means a is going to be the square root of 0 plus this squared and take its square root. So of course that just gives us back this value since a1 is 0 here. So our a in this case is going to be the same as a2, but that's not always true, so you have to be careful about that. So that will be the 0.2993. And now remember this involves e to the negative sigma t, so we could also take sigma as being 1 over tau, just as a conventional form. I mean, you can leave it as sigma as you want, but Circuit Tutor actually asks you to put it in as a form of tau because it's in the denominator. So the tau here clearly is just going to be 1 over sigma, so that we can put it in the form e to the negative t over tau. So we need to take the reciprocal of the sigma value, which as I said, we can compute that, and that worked out to be the 0.2591, and that's a nepper per second. Remember, a nepper it's kind of like a radian, except it's for basically things that don't multiply j in a complex exponential. So this is like for the exponent in a real exponential has so what we call neppers, which is again similar to radian. So it's really just inverse seconds. And so taking the reciprocal of that will give us seconds, and so 1 over 0.2591. That's going to give us our value of tau, which will be 3.86. So just computing that. So the 3.86 again is just the reciprocal of the sigma here, just 1 over 0.2591, and that will give us a number in seconds. Okay. Now the coefficient of the cosine is going to be the coefficient of t, I should say, inside the cosine is omega d, and we've also calculated that from this formula that was shown here based on omega naught, which was first found and then it was plugged in to get here. So omega d, remember, is 0.3645, so that's going to be 0.3645. And of course, if you're doing this all on paper, then you'd have that written down. Again, it's not going to be shown here. And then the last thing we need is our phi value, which uses this so-called atan2 function, which is discussed in the tutorial. But basically, if the real part is non-negative, that's just equivalent to the arctangent of a2 over a1. So a2 is some number, a positive number, a1 is 0, so that gives you positive infinity basically. So the arctangent of positive infinity is plus 90 degrees. Because remember, that's where cosine goes to 0 and sine goes to 1 basically, and that corresponds to 90 degrees. So using this formula then, you'd find that phi in this case would be plus 90 degrees. And this is minus phi in the formula, the way this formula is written, and so that's going to be minus the 90 degrees. If the angle turned out to be if the angle turned out to be minus 90, then you would put a minus 90 in there, and it would be minus would give you the plus. Okay, so that's basically it there. And we've put everything we need, so now we'll just check that. And that is in fact correct. Okay, and now we're basically done, so we just click no more equations here. And at this point, it will offer to show you the detailed explanation if you were unclear on any of those steps. If you just click yes there, it's similar to what you'd get if you give up. So it does give you this interface where you can, so if you just wanted to see, for example, a certain step that you didn't understand, you could choose that, or you can choose all of them as done by default. I'm just going to skip this right now, but basically we're done.